In this video, we're going to start talking about motion in two dimensions, right? So in that motion, there is two coordinates, x and y, right? So we have x and y, and we have an entire plane where the motion occurs. So we need two numbers to specify the position. We need the position, the x coordinate of the position, and the y coordinate of the position. So all the quantities that we've defined, displacement, velocity, and acceleration, now they'll become vectors. The speed is going to still be a scalar, but the displacement and the velocity and the acceleration, they are vectors. Here we have examples of motion diagrams of a car that is taking a curve, right? So it's going through this bend here, and then you can see the displacement vector, right? This is the displacement vector, and here these green vectors, these are the velocity vector. So that's those two diagrams show how to use vectors in motion diagrams. So in general, so you'll have a displacement vector, and then you divide that displacement vector by your time interval, and then you get the vector that goes in the motion diagram, and it typically is going to have the same direction as the displacement vector. Of course, you need a time interval, and so the key, the very important quantity that we need to learn to calculate is the acceleration. The acceleration can be tricky. So remember how we define the acceleration. Acceleration is what? Is the change in velocity, delta v, divided by the time interval, delta t, right? The change in velocity is final minus initial, and the time interval is t final minus t initial, so that's delta v over delta t. So how does that look? How do you do this type of calculations when it comes to two directions or the two dimensions as we have it in a plane? So let's say here, let's look at this graph here. So we have an initial velocity, this vector here, and a final velocity, right? So then the acceleration vector is what? Is the final velocity vector minus the initial velocity vector divided by delta t. So we need to calculate this thing here at the top, right? This subtraction. So we need to do this vector minus this vector. And remember how we did that before, right? So we take this vector, and then we take this other vector here and we flip it around, right? So this is minus v, and now vf minus v would be a vector that goes from here to here. This is delta v. And now we take this vector delta v and divide by delta t, and we get the acceleration, which is this vector here. So this motion from here to here to here has this acceleration that we just calculated. All right, so now that we know about acceleration in two dimensions, we are going to do a very classic problem in two dimensions, which is projectile motion. In projectile motion, this is like throwing a rock. We would have a trajectory like that, and we have two motions here. We have one motion in this horizontal axis that is typically going to be your x-axis, and we have another motion in this y-axis here. So we have these two motions and we have to combine them, and you're going to see that there's going to be vectors all over that are going to help you explain this type of motion. So here we have a stroboscopic of a free falling in the red case, and this one is throwing horizontally. And then you can see, one thing that you can see from this picture is that all these lines are the same. So basically the motion in the y-axis, in this axis, is the same no matter how this thing is falling, right? So the vertical motion of the two balls are the same. So the vertical motion is not as affected by this horizontal motion. There's two motions here, right? So this vertical motion and this horizontal motion. And this seems to be independent on how you throw the rock or the ball this way. So one way to say this is that the horizontal and vertical components are independent. They don't affect each other. So let's look at a motion diagram of a projectile motion. You start here with some initial velocity, and these are your velocity vectors. And if you did that calculation, right? So let's say you take this vector minus this vector, you would get this vector here divided by delta t. If you take this vector minus this vector, you would get this vector here. In all cases, you'll get the same vector a. So that is telling you that the acceleration is always a vector that points in the same way, which is what you would expect, is gravity, right? So the acceleration is a vector that points down. It has a magnitude minus of g, and typically you write it as the vector that points down in the negative direction, if you choose to do so. So a general projectile motion has a few quantities that we need to analyze. So we would like to know the angle at which it is thrown. There's also the initial velocity that can be broken into two components, the horizontal initial velocity and the vertical initial velocity. There is a range, how far it goes, right? And there, of course, there is theta, which is the launch angle. So if you look again at this motion diagram, let's say you throw this ball with some initial velocity. So the initial velocity has a component in the x direction and has a component in the y direction. As it moves, this component in the x direction never changes. You can see that it has the same value. And that is expected because there is no acceleration in this axis. The acceleration occurs only in the vertical axis. If you look at the vertical axis, the velocity starts very high, it decreases, goes to zero, and then becomes negative, right? So that is because there is acceleration in the vertical axis, and that is the acceleration of gravity. So what we can say then is that a general projectile motion is composed of a free fall motion that has an acceleration of minus g, and a uniform velocity motion in the x direction. Okay, so the horizontal motion never changes, and here you can see the vertical motion is a free fall motion. So these are the equations here for the study of projectile motion. So now this is a two-dimensional motion, so we need equations for the y coordinate, and we need equations for the x coordinate. In the x coordinate, there's no acceleration, so the velocity is always constant, is always the same, and then you can use this equation here to find the final position if you know the velocity in the x-axis. In the y-coordinate, it's a motion with constant acceleration. The acceleration is minus g, right? And these are the three equations that we're familiar with applied to free fall motion. Okay, so let's look at one example to see how this all comes together. So you have a sport dog jumping. So basically dogs run at full speed and then they jump. So it is kind of like this. So you have a dog here that is running at full speed, and then they jump and they fall here in some water, and they don't get hurt, of course. So run at full speed, and then they fall in a pool of water, and the winning dog is the one that can fall the farthest, right? So if the speed is 8.5 meters per second, that's a typical speed for this event. So, and the height is 0.61 meters, 2 feet. So how far do they go? So then this is a projectile motion problem. So let's look at the picture. So that's a strategy we're going to use here. So this is the picture here. So the dog is coming running this way. So it jumps. So it has this initial velocity, which is just a horizontal velocity. And it's going to have this motion here, which is a projectile motion. The acceleration is the acceleration of gravity minus g. So here we have the initial state and the final state. So here we have x initial, y initial, time initial, and initial velocity in x and initial velocity in I. 5 things that we know or we would need to know here, and then 5 things here that and these 5 quantities are related to these 5 equations that we looked at before. Let me show you the equations here. So we have these 5 equations. So what do we know? Well, we can set our coordinate system here. This is our x, this is our y. And we can start looking at the initial position x. The x coordinate of the initial position is 0, right? It's this point here. The initial velocity in y is 0 because it's not jumping up or down, he's just going straight, right? We can always set our clock t equal the initial time to be 0. So the initial position in y is going to be this here, right, which is 0.61 meters. And the final position in y is 0 because it comes down here. The initial velocity in x, which is equal to vi, is 8.5 meters per second. There's no acceleration in the x-axis, and the acceleration in the y-axis is minus g. What do we want to find? The range, which is this distance here, which is also xf. That's what we want to find. So how do we find that? Well, we have everything we need to know here. So we have our picture. So we just need to look at our 5 equations and see how to do this, right? So we start by using this equation here, which says the final position, vertical position equals to initial vertical position, initial velocity times delta t minus 1/2 delta t squared. What is my final position? Is 0. My initial position was 2 feet, 0.61 meters. I have no initial velocity in the y direction, so this is 0 here. And then this is minus 1/2, 9.8 times delta t squared. So now from this here, I can solve for delta t, right? So I would have 0.61 minus 1/2, 9.8 delta t squared, and this is delta t here, I forgot that. Delta t times 0.61, that's equal to 0. That's that equation. So this delta t cancels the square there, and I get that delta t is equal to 2 times 0.61 divided by 9.8. And that gives you this number here. And now that we know the time, we can use the position for the horizontal coordinate, the equation for the position, to solve for the final position. So the final position, which is what we want, is the initial position plus the velocity in the y-axis, in the x-axis. This is Vx initial, that never changes because there's no acceleration in the x-axis, times the time. And that gives me 3 meters. And that's the distance that this dog jumps.